Hi, everyone, and welcome to this episode. Today, we are studying for the AP Chemistry exam, and in particular, we're studying Unit 8. So, this is a review video for the entirety of Unit 8. And Unit 8 is kind of a big one. It's one of the culminating units of AP Chem. And so, there's a lot going on, a lot of things we have to know from prior units, and put it all together in this unit on acids, bases, and buffers. So there's a lot going on, but we'll get into it. We're going to be studying these topics: 8.1, Introduction to Acids and Bases; 8.2, pH and pOH of strong acids and bases; 8.3, weak acid and base equilibria; 8.4, we get an introduction to acid-base reactions and buffers; 8.5, we'll take a break and talk about acid-base titrations; 8.6, molecular structure of acids and bases; 8.7, pH and pKa; 8.8, properties of buffers; 8.9, the Henderson-Hasselbalch Equation, wonderful name there; and 8.10, buffer capacity. These are the 8 subunits found in the AP Chemistry curriculum, and we're going to get to all of those. I want to make a note that I have videos that contain information about all of these separately, and you can find them in my playlist under Unit 8 AP Chemistry. So if you'd like some more detail on these topics, go there. I will be using some of the slides and examples from those videos, but like I said, if you want more detail, you can head over there for some more. All right, let's get into it. First of all, I just wanted to start with the definitions of acids and bases. You can't do much with acids and bases unless you know what they are. And we define them in a couple of different ways. Bronsted and Lowry definitions are that acids are proton donors. So if you see a chemical reaction and there's a hydrogen swapping places, the one that gave it away is your acid. The one that accepted it, it's your base. And Arrhenius has a related definition. Acids tend to produce H plus or hydronium ions in water. Bases produce OHs in water. And we also have to know the difference between a strong acid and a weak acid. Strong acids dissociate 100%, and if we start thinking about them as equilibria, setting up equilibrium from both sides, these acids, these strong acids, have very, very large Ka values. In fact, so large they're usually not even mentioned because they're just 100. We're assuming 100% dissociation on those. And weak acids, because of their structures, end up dissociating less than 100%. So maybe only a small fraction dissociate and make hydronium ions. But those are governed by Ka values, which you can find in tables either in your folder or on the internet or in your textbook. Okay, so to sum up, a strong acid is one where the acid dissociates 100% and the equilibrium lies far to the right, so large K value. And a weak acid is one where the acid dissociates less than 100%. The equilibrium lies far to the left. The concentrations of hydronium ion and hydroxide ions, this is still in 8.1, are often reported as pH and pOH respectively. Keeps the numbers nicer so we're not writing scientific notation all the time and dealing with numbers that are extremely small. So the pH is defined as the negative log exponent of the H3O plus concentration, and the pOH is the negative log of the OH concentration. A quick note from the lovely people at the College Board. The term hydronium ion is preferred, but they will accept hydrogen ion on the exam. If you have gotten used to that or if you put it there inadvertently, you should get credit for that. Let's talk about water and how amazing it is. Water ionizes with an equilibrium constant Kw. It's so special, it gets its own value. Kw is equal to the H3O plus concentration times the OH concentration. And that's equal to 1 times 10 to the minus 14th at 25 degrees Celsius. More on that in a minute. In pure water, the pH equals the pOH and is called a neutral solution. And since pH and pOH are both 7, they add up to 14, and that is one of our relationships. The pH plus the pOH is equal to 14. Here's a fun little visual of the autoionization of water. Water just does this naturally. You can imagine water molecules bumping around, banging into each other, and at one point, one of them just drops a proton and gives it to the other one. And you have a hydronium and a hydroxide in equal amounts, equimolar amounts. And they naturally do this to some small extent. 1 times 10 to the minus 7th moles per liter in neutral regular solution. I'm going to include this because you're likely to see some questions about this. Turns out I'm going to break news to you. We all think the pH of pure water is 7. And that is true at 25, but not at any other temperatures. It's weird that the pH of water can actually be something different than 7. Okay? And the reason is because the Kw value that governs the dissociation of water is actually increasing with increasing temperature. So, as all equilibrium constants are temperature dependent, we get this increase. So this actually is an endothermic reaction. We learned in unit 8 and 7 that endothermic reactions have K values that increase with increasing temperature because added heat drives the reaction to the right. And so we get this situation where at 50 degrees Celsius, it might be 5.48 times 10 to the minus 14th. And so if you take the square root of that, you would get a value of like 6.63 or something like that. You would actually have a pH that's lower than 7, even though it's neutral because both H and OH are being produced. So that's a little mind boggler for you. Okay, we're going to head into 8.2, the pH and pOH of strong acids and bases. So molecules of the strong acids, we're going to start with those. These guys, these 6, will completely dissociate in solution to produce hydronium ions. The concentration of hydronium ion is the same as the concentration of the initial acid because they dissolve completely, dissociate completely, and thus the pH can be easily calculated. I'm going to show you a couple examples, and we'll have a pause the video mode. How to calculate the pH of strong acid solutions. If you'd like to write this down, feel free. Find the molarity of the strong acid in the solution. Maybe it's given to you. Maybe you have to find moles and find liters and divide it. But you find the molarity. Since they dissociate 100%, whatever the molarity of your acid is, let's say you get that, is then going to be equal to the molarity of the hydronium ion. So you just match it up. And then if you take the negative log of the H plus or the H3O plus, you'll get your pH. So here's a couple examples I used in one of my segmented videos. So we'll just throw it up there for the sake of time. Again, if you'd like to see the full solution and extra practice, you can go to the other videos. HI, friendliest acid in the whole world because it's always saying hi. What are the major species present in a 0.202 molar solution of HI? When this dissolves, there's actually going to be none of that left over. They're all going to be iodines and hydroniums, and of course the water is floating around in there as well. What's the pH of this solution? Well, if I know the pH of the acid, I know the pH of the hydronium, just equal amounts, and I take the negative log of that to make 1.7. Okay, your turn if you would like to. What are the major species present in a 0.003 molar solution of perchloric acid? What's the pH of this solution? Feel free to pause the video and come back in a couple of seconds. And if you pause the video and calculated a pH of 2.52, then congratulations, you're off to a great start. Okay, let's go into bases. pH and pH of strong acids and bases. Strong bases, which you have to know are the hydroxides of the group 1 and 2 cations, will completely dissociate in solution to produce hydroxide ions. The concentration of hydroxide ion is the same as the concentration of the initial base, doubled for the alkaline earth metals because they have an OH parentheses 2 in their formulas, so make sure you know about that. And thus the pH and pOH can be easily calculated. It should be noted that the hydroxides of groups 1 and 2 on the periodic table are listed by the College Board as being strong bases. And that is in contrast to other sources, like one that I saw that said just the alkali metals or the group 1 hydroxides are strong bases, along with barium hydroxide, which is mostly soluble. But there's some kind of debate about strontium, calcium, and magnesium. So I guess it's one of those raging debates in physics where there's a lot of yelling and throwing of things, and we'll maybe eventually get it done. But the College Board does consider both columns, groups 1 and 2, to be strong. So there you have that. And how to calculate the pH of the strong base solutions? You basically just have to find its molarity again, double it for those alkali metal hydroxides, find the pOH from the OH concentration, and then you can subtract it from 14 to get the pH. So let's look at a couple examples here. What are the major species present in a 0.05 molar solution of sodium hydroxide? Once again, realize that there's going to be none of those left over. They're not together anymore. They've all dissociated along with some water. Those are our major species. The pOH is the negative log of its concentration. That's 1.30. Subtracting from 14 gives me 12.70. And if you're so inclined to try it yourself, here is another one. This is lithium hydroxide. So take a moment, pause the video, and see if you can solve it, and be back here in a couple seconds. All right, and the pH for this one comes out to be 11.6 on that. It's slightly less concentrated than the sodium hydroxide, so a slightly lower pH on that. So good luck. Good job if you got that. Now let's move on to section 8.3, weak acid and base equilibria. So most of what we do in this chapter is weak acids and bases. All right, so let's read what the College Board says. The solution of a weak acid involves equilibrium between an unionized acid and its conjugate base. The equilibrium constant for this reaction is Ka and is often reported as a pKa. Again, pKa is the negative log of the Ka value. And in general, we have the weak acid in equilibrium with some hydronium and its conjugate, and these weak acids have Ka values, and there's the expression. So if you're ever asked for the Ka expression for a weak acid equilibrium, use this. This is your expression, and if you know what the anion is, substitute it in there, and like nitrate or something like that. No, not nitrate. Nitrite would be a better example. Okay, now weak acids have Ka values that you'll either be given or you can look up on the internet or in a table that you might have been given. All of these are weak and have varying Ka values. The strong ones have large Ka values, and so they're typically not listed. And as far as overall acid-base strength goes, as acid strength increases, the Ka and the H plus also increase. The pH is opposite of that. It decreases because with a larger Ka value, if you take the negative of the exponent, you get actually a lower value. And the opposite is true. As base strength increases, Kb and OH increase, pH increases as well. And I'm just throwing in some tools that we use. You'll be given these types of things if you ever need them. But again, be reminded that the Ka for an acid times the Kb for its base will always equal Kw for water at that temperature, which we learned that at 25 degrees Celsius is 1 times 10 to the minus 14th. So plan on using that one. Okay. In our video on weak acid problems, I actually did 4 different kinds. Today, I'm only going to do one of them, and that's the first one. If you need examples of finding the Ka value using the pH, finding percent ionization, or the Ka using percent ionization, you can go to that video on weak acid. You'll find it in the Unit 8 playlist. Okay, typical problem you're going to see. This is most common. What are the major species present in a solution of acetic acid? Now, you've probably done this one. Acetic acid is very common, but the same thing would happen for any other weak acid. So calculate the pH of a 0.1 molar solution of acetic acid. You're going to need to do an ice table for a weak acid, and it helps to set up the reaction. Acetic acid plus water makes acetate plus hydronium, and then the ice table. Initial, 0, and approximately 0, minus x plus x plus x. Get your x terms. Set them equal to the Ka value, which is 1.8 times 10 to the minus 5th. And if you solve for the x, which is the H3O plus concentration, you get a number. And if you take the negative log of it, you get 2.87. So I whipped through that pretty quickly. But if you want to pause the video, feel free to do that. And if you want to, try one on your own. We have a 1 molar solution of HCN. If you'd like, take a moment and see if you could find the pH of this solution. And if you did that and you're back, I got a pH of 4.6 because it's a slightly weaker acid than the acetic acid. Okay, same idea, same reaction, except the cyanide instead of acetate. Same ice table type thing. The Ka expression set the equal to the x terms. X was 2.48 times 10 to the minus 5th, and the negative log of that is 4.6. So good job if you were able to do that one. And still in 8.3, let's talk about weak acids and weak base equilibriums. A solution of a weak base involves, you'll notice the similarity in phrasing here between a weak base, a proton acceptor, and its conjugate acid. The equilibrium constant for this reaction is Kb, and it is often reported as pKb, the negative log of Kb. Here's your general equilibrium reaction. Base plus water makes the conjugate acid and the OH, and its conjugate and its equilibrium constant expression. Okay. And just like with the weak acids, I'm only going to do one of the three. If you like examples of these other ones, you can head over to my video on weak base equilibrium problems. But to get us started for today in our review, we'll do the most common kind, and that's finding the pH from the Kb value. So in this case, calculate the pH of 0.01 molar ammonia. So NH3 plus water makes NH4 plus and OH minus. That's our reaction. And 0.1 is 0.1 is our concentration, 0 at approximately 0. We do all the X terms like we do normally. Kb, set it equal to the Kb a value, 1.8 times 10 to the minus fifth. And we get a pH of 10.62 because when we get the OH, we get a number. The pOH is the negative log of that number, which is 3.37. And the pH is 14 minus the pOH, so 10.62. And if you are interested in continuing on and trying one of your own, here's example 2 under bases, finding the pH of a 2 molar solution of hydrazine. Take a moment, pause the video, and be back in a couple seconds. And when I did this one, I got a pH of 11.39, not as high as the ammonia. No, actually a little higher than ammonia, sorry. Because its Kb value was a little bit higher than ammonia's. Okay. My X value was 2.45 times 10 to the minus 3, and those are the concentrations of everything that's there. Notice that the hydrazine still remained around 2 molar. If I only take this much away, it's still about 2 molar. And finding the pH the same kind of way. All right, let's talk about percent ionization for a moment. This is also part of 8.3. And the percent ionization of a weak acid or base can be calculated from its pKb and its initial concentration. And here's the formula you're going to want to remember. Amount ionized over the initial amount times 100. And what do we mean by the amount ionized? That's X. When you get your X value, that's how much ionized from the original thing, divided into the original amount, and get the percent from that. Let's look at a couple examples. What is the percent ionization of ammonia in example 1 that we just did? So I'm going to keep that continuing on. Percent ionization is the OH over the NH3 original. The X value is 4.24 times 10 to the minus fourth over the original, and I get 4.24%. And if you did the hydrazine example, feel free to pause the video and calculate the percent ionization of the hydrazine. And if you did that, and you found that it's a lot less, 0.123% ionized, then congratulations, you did it right, and you're well on your way to mastering acids. Before we leave section 8.3, which is probably the most dense section in this entire unit for the types of problems and the amount of problems that you're going to see, we need to talk real quick about acid-base properties of salts, which are the conjugates of the acids and bases that we've already talked about. And it gets kind of complicated in here. Again, I have a separate video for this, but we'll hit the highlights here. It turns out that some ions actually do affect the pH. Even when there's no apparent hydrogen or OH being present, they go into the water, the pH changes. So how does it do that? Now, you may have been given a chart of ions that actually act neutrally, cations that act neutrally, or some that make the solution basic and some that make the solution acidic. But you also have to kind of understand how and why they do that. It turns out that some ions, like the phosphate in my original picture, are actually conjugates of weak acids or bases, which means that, for example, phosphate is the conjugate of a weak acid, and it would actually rather exist in equilibrium with its conjugate acid. So some of them take hide protons off the water molecules, returning them to the weak acid that they came from, and now you've produced an OH, which actually changes the pH. Okay, so how do you make sense of all of this? Again, there's more in the original video. But you might be presented with a question like this in your textbook or one of these individually on an AP exam. Will aqueous solutions of the following be acidic, basic, or neutral? Or they might say, which of the following might be acidic, which one might be neutral, or whatever. So I've developed this little chart, and hopefully it's helpful for you. And the way this chart works is if you have a salt in question, just maybe pencil it in. You can copy this down, make copies if you want. And then split it into its cation and its anion. And then use your powers of imagination to imagine the cation has an OH next to it and the anion has a hydrogen attached to it. And then ask yourself, is this a strong acid or base? And is this a strong acid or strong base? Sorry, let me start over. And then ask yourself, is this a strong base or a weak base? And is this a strong acid or a weak acid? If it's a strong base, that means that cation is the conjugate of a strong base, and it's not going to want to get back together with an OH, so nothing's going to happen. But if it's a weak base, the cation will actually want to get the OH back, and it will act as an acid. Okay? And if it is a strong acid, then it's not going to affect the pH because its conjugate ion is very, very weak, and it's not going to do much. It doesn't want to get its hydrogen back. And if this is resulting in a weak acid, it'll make the solution basic because it'll want to get that proton back and exist in equilibrium. Okay, so a couple examples I used in my original video: potassium phosphate. Potassium hydroxide is a strong base, so potassium will not affect the pH. But phosphate is the conjugate of a weak acid, so it will affect and make it a basic solution, and it'll actually make it basic using the diagram I just showed you. And the opposite would occur with something like ammonium chloride. Ammonium hydroxide is one of the weak bases. And so weak base, the cation has an extra proton. It's going to act like an acid and give it away. And chloride is the conjugate of hydrochloric acid, a strong acid. And that means the chlorine will not affect the pH because it will not gain any hydrogens back. So in summary, if you want to pause the video and write these down, conjugates of strong acids or strong bases have no acid-base properties. Conjugate bases of weak acids will make the solution basic. Conjugate acids of weak bases will make the solution acidic, opposites. And if both an acid and a base are present, the one with the higher K value will dominate. You probably won't see that, but just wanted to throw that in there. Okay, you might be asked to find the pH of a salt solution. And in order to do that, you need to determine what salt you have. And using the chart I just showed you, identify which ions have acidic or basic properties. You'll want to write the equilibrium equation for that. Then use Ka or Kb values to determine K for the equilibrium. You're going to solve for either the OH or the H and find the pH from that. A lot of steps, I know. It gets kind of complicated and crazy. Here's the example I used in my original video. Calculate the pH of 0.1 molar sodium acetate. Now, acetate is the conjugate of a weak acid, so it's going to act like a base, reacting with water to produce acetic acid and OH minus. Do a regular ice table, but now I need the Kb, not the Ka for the acetic acid. But that's Kw over Ka, 5.6 times 10 to the minus 10th. Now I set it equal to my equilibrium expression, and I solve for X, which is the OH concentration here. Get the pOH of that, and the pH is 8.87. Okay. And if you are interested at all in trying one on your own, here is one to calculate the pH of NaClO, 0.2 molar. Pause the video. See you back here in a couple seconds. And if you were able to do it and get a pH of 10.41, then congratulations. You are, again, on your way to mastery. And now heading into section 8.4, acid-base reactions and buffers. Here is what we find in the study guide. When a strong acid and strong base are mixed, they react quantitatively in a reaction represented by the equation H plus OH makes water. The protons and the hydroxides have a party. They get together. They make a bunch of water molecules. The remaining ions are spectators, and that's your net ionic equation. The pH of the resulting solution can simply be calculated by the concentration of whichever one of those is left over. They'll annihilate each other as much as they possibly can, leaving behind one or more of the others, and you just find out how much it is and take the negative log of it to get the pH or the pOH, respectively. All right. And then we get this statement. When a weak acid and a strong base are mixed, so you have to recognize I might have a weak acid and I'm dumping a strong base in there. What's going to happen? They react according to the equation HA plus OH minus. The OH is going to react with the weak acid to make its conjugate and water. Okay, and then you got a couple of options. If the weak acid is still in excess, like I haven't neutralized all the weak acid yet, then a buffer is formed because now you're going to have still some weak acid and its conjugate, and that is a buffer solution. The pH of the solution can be found using the Henderson-Hasselbalch equation. We'll look at that. If a strong base is in excess, that means we've annihilated all the weak acid. And so you just have a bunch of OHs floating around. They're going to dominate the pH of the solution. And if you find the molarity of that, you get your pH or pOH. Okay? And if they happen to be equimolar, like if I'm doing a titration and I get to the equivalence point and I've neutralized all my acid, then what I'm going to have is simply its conjugate base, which is going to act like a base and produce a slightly basic pH at that equivalence point. So the anion will reset up an equilibrium with the conjugate acid, producing some OHs. All right, and the opposite happens when a weak base and a strong acid are mixed. You'll see some similarities here. The weak base and some hydroniums are going to react to make the conjugate acid of the base and some waters. And again, if the weak base is in excess, a buffer is formed. We haven't neutralized it all yet. If the strong acid is in excess, that means we've neutralized all the base and we just have excess acid in there, and so we can just find the negative log of the concentration. And if they're equimolar, we get to the titration, the endpoint of the titration, and we've produced all HB pluses, which I converted into HAs now because they're conjugate acids. It will then reset up an equilibrium with the anion, the conjugate base, and some hydronium ions, and you'll get a slightly acidic pH out of that. Let's take a look at some diagrams to illustrate how this is done. This diagram I made, and it's got some buffer in there with some weak acid and its conjugates, 4 of each. Okay, and if I add hydrogens to it, like I drop in a couple of hydrogens, some protons, what's going to happen is the protons are going to react with the acid, the base, the anion, and produce 2 more of the weak acids. Now there are 6 over here and not just 4. And there's 2 less of the anions, the conjugate bases. So this is the reaction that's going to occur if I add acid to it. On the other hand, if I add base to it, some OHs, so let's say I add some OH here and another OH here, what's going to happen is the base is going to drop in, look around the beaker and see what's there, and it's going to react with the best acid available, and it's going to take the protons off the weak acid to make some waters. Let's pair up those, and we'll end up with 2 more anions or conjugate bases that we didn't have before, a couple of water molecules and 2 less of the HAs. It should be noted that the more of these that are present, the more additional acid or base can be neutralized because you have more molecules. That's called buffer capacity. Okay, and here's a diagram that I made that's similar to what you might see on an AP exam as well, with just the molecular models. So we have to kind of be able to do the same thing. So if we add in a couple of protons, those protons are going to hook up with some of those anions and make a couple more over here. Same reaction. And if I add some OHs, let's make them fully in there and another fully one. And what's going to happen is that they'll hook up to make some water molecules, leaving behind a couple more of the anions. So we have to kind of conceptually think that through as we go through our sample of buffers. Now let's do a couple buffer calculations. Again, this is a repeat from an earlier video, but if you've never seen that video, you can always go there or stay here and check this out. What's the pH of a solution containing 1 molar HF and 1 molar NHF or NaF? What you have to do is be able to recognize the fact that there's a weak acid in a big concentration and its conjugate, the F- ion. Okay, now there are 2 ways to do the pH of a buffer. One the long way and one the short way. So here we go. You can set up an ice table for that weak acid, like normal. Put your initial concentration of the acid, but also there's going to be an initial concentration of the conjugate base. So you can put that in there. set your X values, set it equal to the Ka value. And what will happen is, in this case, the concentrations of the F and the HF are the same, so they end up canceling, and the X is equal to the Ka value. And that's 7.2 times 10 to the minus 4th. And the pH is negative log of that, or 3.14, which is, coincidentally, it's pi, but only the first three digits. And pH is 3.14, pKa is 3.14. Is that a coincidence? No, it's not. pH will equal the pKa when both concentrations are equal. Okay. And what you can do then, I want to show you what will happen if you're asked. I'm told there's less likely that you'll be asked to this on an AP exam now, but let's calculate the pH change when 0.01 moles of sodium hydroxide is added to that buffer solution. What reaction will occur? Let's figure out the new concentrations and do the stoichiometry. Here's what you got to do. You have to think to yourself, the OH is going to go in and react with what? Who's at the party that it's going to react with? The HFs. The HF plus the OH are going to react to make some water and more of the fluorides. Now, there was originally 1 molar of both of those, but now I'm adding in 0.01 molar sodium hydroxide. So this is going to react to completion. So this is going to go down to 0. That's going to go down by 0.01. That's going to go up by 0.01. And now I have two new concentrations. See how I did that? And then you can go back to your equilibrium expression to calculate the new pH. Ka equals 7.2 times 10 to the minus 4th, 1.01 over 0.99. Now they don't cancel equally, times the X value. The pH went up slightly to 3.15, but not much because the ratio of these two did not change. Okay, and I know there's a whole section later on that called the Henderson-Hasselbalch equation, but here's a good part to introduce it, because when you do buffers, it's a huge time saver. And the Henderson-Hasselbalch equation basically takes this and takes the negative log of both sides, and you end up with the pH equaling the pKa plus the log of the ratio of the conjugate base over the acid. The ratio. Not necessarily the molarities, the actual ratio. So what I'm going to do is I'm going to go back to the original problem I just did in two parts and do it again using Henderson-Hasselbalch. Okay? What's the pH of a solution containing 1 molar HF and 1 molar NaF? If you recognize this as a buffer, and hopefully you do, you can say, oh, all right, I know it's a buffer, so the pH equals the pKa, 3.14, plus the log of the ratio of both of those. And if you have an equal amount, regardless of molarity, the ratio is 1, the log of 1 is 0, and you end up with pKa plus 0, which is the pKa. Kind of convenient. I really like that. And if you want to calculate the change that occurs, you can go back and do the stoichiometry and find that one of these is going to go up by a certain amount, one of these is going to go down by a certain amount, depending on your reaction. But once you find those amounts, just plug them back in. Now I have a ratio of 0.101, and if I add the log of that to 3.14, I get 3.15. So same answers, one's more of a long way, one's a shorter way. All right. And section 8.5, acid-base titrations. We're told that an acid-base reaction can be carried out under controlled conditions in a titration. A titration curve plotting pH versus volume of titrant added is a useful summary of a titration. And here's one showing the titration of acetic acid, which is a weak acid. So typically, a weak acid will start at a lower pH, not hugely low pH, and it'll pop up, and then it'll have this flat region called the buffer region. And that's what happens when you start neutralizing a weak acid and turning it into its conjugate base. And during this region, you actually have both, some weak acid, some conjugate base, and the pH doesn't change much because it's a buffer. It should be noted, we'll come back to this actually in just a second. At the equivalence point, the number of moles of titrant is equal to the number of moles of analyte originally present. Using stoichiometry, this relationship can be used to determine the concentration of the analyte. So it's just when you do stoichiometry calculations, they're stoichiometry. So try not to make them too complicated. You'll recognize the equivalence point of a titration when the graph gets steep. And halfway up that steep section, that's the point of your equivalence. The pH is changing rapidly, and that's how you know. Okay, so more on that in a little bit. Titrant. Let's talk about some acid-base vocabulary. You'll see words like titrant, and that is the liquid being added to the unknown. That's the stuff that's in your burette. The burette is your item of glassware made for dispensing accurate volumes. The end point, or the equivalence point, the point at which the number of moles of titrant equals the number of moles of the unknown. This is usually signaled by a color change using an acid-base indicator. And the analyte is the liquid that's being tested. So when you do a titration, you're pretty much going to have it set up something like this. You're going to put your analyte in your flask and your titrant in your burette. You're going to add it. You're going to need the initial volume and the final volume of your solution. So when you're asked what measurements do you need, don't just say the volume of solution. You need the initial and the final because those are your actual measurements, along with the measurement of your analyte. Okay? And when you do titrations, especially weak acids and bases, it is really cool and important to consider the pH halfway to the equivalence point. This is huge, guys. So pay attention. At this point, if I've neutralized half of my weak acid, I have now produced an equivalent amount of its conjugate base. That means the ratio of the acid to the base, or the base to the acid, is 1. They're the same. And that means the pH equals the pKa at that point. Okay, it's a magical time during a titration. And I always tell my students, if you know it's coming, you can listen for it. And if you get to that point, you can almost hear the little molecules. They're happy. They're singing songs and holding hands and dancing around in circles because they've reached this magical point where the pH of that solution now equals the pKa of the acid that's doing it. Okay? And that, I think, is really fun to think about. And if you ever saw a graph that looks like this with some kind of weird, humpy looking things there, that means you're looking at a diprotic or triprotic acid. And what happens is, in a titration, let's say you're titrating oxalic acid, which is H2C2O4. After you start, right as you start, you're going to end up with H2C2O4, but you're going to produce some HC2O4 minus, and they're going to actually make a little buffer region right here as you go along. The pH is not changing much. Once all of this is gone and you have only this, the pH is going to jump up slightly, but as you titrate that, you're going to get an equilibrium between this weak acid and its conjugate base and a second buffer region right here. And the pKa of the original acid is right there, halfway to that first equivalence point. The pKa of the second one is the pH halfway through that region. And that was a lot of information condensed there, but that's how you might read that. So pH and titrations. And now moving into section 8.6, molecular structure of acids and bases. And this gets at the ideas about why some acids are weak and some acids are strong. And we'll start in. The protons in a molecule that will participate in the acid-base reactions and their strengths can be inferred from molecular structure. What's the molecule doing? Strong acids have very weak conjugate bases that are stabilized by electronegativity, inductive effects, resonance, or a combination of both. Maybe the conjugate base has a bunch of very electronegative atoms to it. And maybe it exhibits resonance, so it's very stable, or some combination thereof. Carboxylic acids are one common class of weak acid. Strong bases are the group 1 and 2 hydroxides, have very weak conjugate acids. So that's what makes them strong bases. Common bases include nitrogenous bases. Lots of molecules have nitrogens in them, and those nitrogens have lone pairs sitting right there waiting to accept protons, and they end up being weak bases in a lot of cases. Electronegative elements tend to stabilize the conjugate base relative to the conjugate acid, and so increase acid strength. Okay, so let's talk about that. I'll summarize what I put in my original full-length video. The two factors that determine the extent to which something acts as a Bronsted acid: the strength of the bond and the polarity of the bond. If the bond between the hydrogen and what's there is weak, it's going to pop off super quick and easy, and it's going to be a stronger acid. If the bond is more polar, meaning there's more electronegative stuff on the other side than the hydrogen, then the bond will be more polar and it's a stronger acid as well. Okay, so in general, although the HF bond is very polar, its high strength makes it a weak acid. We talked about this. Hydroiodic is strong. Hydrobromic is strong. Hydrochloric is strong. But hydrofluoric? That's actually pretty weak. Even though the bond between these is very, very polar, H and F, fluorine is the most electronegative element, it actually, because of its small size, snuggles really close to the hydrogens, making a very short bond length and a very strong chemical bond, so it ends up being a weak acid. So there's bond strength at play there. In general, though, if you want to know if something's more strong of an acid, you look for, first, more oxygens. Turns out that things like H2SO3, that's weak. H2SO4, that's strong. Because there's more oxygens pulling electrons closer to them and away from the hydrogen pops off. Same with the chloroacids. HCl, pretty weak. HClO2, HClO3, now we're getting stronger. By the time we add that fourth oxygen, we have a strong acid with all those electronegative oxygens on it. Same with nitric acid. Nitric acid is stabilized by its resonance, and it has 3 oxygens on it along with the nitrogen, which is fairly electronegative. And those electrons get attracted over here to make a stable anion, and the proton goes over here to make a hydronium that way. Now, nitrous acid, not quite so lucky. It's only got 2 oxygens, so not quite as strong of an acid. And you can even have some that are not included in our list of strong acids, but are kind of fairly strong. This one actually happens to have 3 chlorines on one end plus a couple of oxygens, so the electrons are going this way. The hydrogen pops off quite easily. And if you need a quick pick of a chart of electronegativities, you can Google that. There's millions of them on the internet, so go make sure you find yourself one of those. And note that the electronegative elements are up here. Those are the ones you commonly find in strong acids. And finally, a quick note about carboxylic acids are very strong. Not very strong. They're very common. And you can recognize them by a carbon in an organic molecule being attached to an OH, that's your acidic proton, and then a double bonded OH oxygen over here, which is very electronegative. It pulls the electrons this way, the hydrogen pops off. This one is more of an alcohol. It doesn't have the double bonded oxygen on this carbon, so that's not going to be a very acidic proton. Section 8.7, pH and pKa. Again, I included the Henderson-Hasselbalch equation over here because, look what it says, the protonation state of an acid or base, the relative concentrations of HA and its base, can be predicted by comparing the pH of the solution to the pKa of the acid. When the pH is less than the pKa, the acid form has a higher concentration than the base form, because now we've got more down here and the resulting pH drops slightly. When the pH is greater than the pKa, the base form has a higher concentration than the acid form, and so the pH is now higher than the pKa that it came from, because you're adding a positive result from this log of the ratio. When the pH equals the pKa, that means they're both the same, and the ratio is base over acid is just 1 over 1, whatever it is. Log of 1 is 0, and so the pH equals the pKa. You're likely to see a question about it during a titration. Let's go back to this diagram for a moment. We've already gotten really excited about the fact that at halfway to the equivalence point, the pH equals the pKa, whatever that is. And before that, we're kind of getting up to that pH value, and after that, we're going beyond that pH value. So before that, we're still a little bit lower. That means we still have more of the acid that we started with, and we haven't neutralized half of it yet, so we don't have equal amounts of its conjugate base. Right there, they're both equal, and remember, all the molecules are singing songs and holding hands because it's the magical time. And then as soon as you get past that, now you have slightly more of the conjugate base than the acid, and the pH continues to rise slightly until you get to that equivalence point when all the acid is depleted. So you might be asked a question about pick a spot on the graph where the ratio is less than 1, or pick a spot on the graph where there's more base than acid, and you can pick appropriately from that. Okay. Continuing on to section 8.8. We're almost done, guys. We actually did most of the work already. Properties of buffers. This goes back to the general ideas about buffers. A buffer solution contains a large amount of both members in the conjugate acid-base pair. The conjugate acid reacts with the added base, and the conjugate base reacts with the added acid. These reactions are responsible for the ability of a buffer to restabilize the pH. And that goes back to the diagrams that I made and showed to you earlier, where you have a buffer with some of both in it, and then you add acid, it makes more of the HA, or you add base, and it neutralizes some of the HA to make more of its conjugate base, effectively turning a strong base into a weak base. That's part of the equilibrium. Okay? And we also saw that in terms of the molecular model drawings. Adding more protons, they react with the anion to make more HA. Adding more OHs reacts with the acid to produce more water and some anions that are there. Okay, general ideas about buffers. We've done some calculations already earlier. Section 8.9 repeats the Henderson-Hasselbalch equation, which we've done earlier in this video. So if you need to, head back to section 8.4. If you jump to this part, you can jump back to section 8.4 and see the calculations involving those. But again, it's just this equation. You'll be given it on your equation sheet. pH, pKa, plus the log of the ratio of the conjugate base over acid, using any units. It could be millimoles, moles, molarities, whatever it happens to be. As long as you know the ratio, that's what's most important. All right, it's a tool that we use. And finally, buffer capacity. Quick note about buffer capacity here at the end of our review. That's section 8.10. Increasing the concentration of the buffer components keeps the pH of the buffer the same, but increases the capacity of the buffer to neutralize added acid or base. And when a buffer has more of the conjugate acid and base, it has a greater capacity for addition of more base than acid. When a buffer has more conjugate base than acid, it has a greater capacity for addition of more acid than base. So for example, if we were to take our buffer and start adding more HAs and A minuses, we would get more of an ability, since each one of those is able to neutralize an incoming acid or base. You have more ability for more H's and OH's to get gobbled up. If there's fewer of these, it has less of a buffer capacity. And there are calculations that go with that, but we're not going to do them here. Okay, so that's all 10 sections of Unit 8 on AP Chem. I admit it, it's a lot. There's a lot going on there. Hopefully you've got some practice before this. If you haven't and you need to go back and see the individual videos, head over to the playlist that this video is a part of, and you'll see some section videos as well as some extra videos about acid-base titrations, how acid-base indicators work, why we can use phenolphthalein when it turns color at a pH of 8 to 10, not 7. So we've got some extra stuff in there as well. I hope you found this helpful. If you have questions, comments, concerns, send them to me in the comments or directly. And in the meantime, happy solving, happy studying, and have a great day.